Kinsley.
Hello, sir.
Yes. So how do I share the screen now?
Sir, please, are you using phone?
Yes.
All right. So you see the three dots. Uh,
Hello. Can you see my screen?
Yeah, we can see it, but the
Yeah, we
slide
can
is.
see it.
Okay. Okay, so this is it, right?
Yes, sir.
Mhm. Okay. All right. So we did a calculation for the resistors, whereby we said the resistor has a first color, which represents a number. Then the second color also represents a number. The third color represents the multiplier. The third color represents a multiplier. Then the fourth one, that is the tolerance, giving you the tolerance of the resistor. The resistor has no polarity, so hence you don't need to know the positive and negative sides of the resistor whilst using it. So where do we find to be the starting of the color code? That's the question. Where can we say that, oh, this is where the color code starts from, so that you know where the numbers are beginning? Usually, the color codes that determine the tolerance are either gold or silver. So that is when you know that it is the end. So the tolerance is the end, whilst the other colors marks the beginning of the resistor. the color codes. So you see that usually, again, the tolerance band separates itself a little away from the other color bands. So that will tell that that is the end. You understand me? The first three bands are usually closer to themselves, and then the last band, which is either gold or silver, separates itself a little from the other colors. Hence, you will know the beginning of the color codes. Please do not bother yourself with the mathematics that is here. The I equal to C dV dt, or V equal to I 1 per C integral of t to 0 I dt. Don't bother yourself with these ones, okay? Okay, so yeah, so that's the conductance. Okay, they say a capacitor is a passive circuit element that has the capacity to store charges or charge in an electrical field. Hey, this is not true. You can take your phone and check how does capacitor stores electrical energy. It stores it as electric charge, not field, okay? It stores it as electric charge. So please, if you have your this thing, you change it.
Yeah,
it's not field.
Yeah, it's charged.
It's a mistake.
It's charged.
Yes, it's a mistake, okay. So stores charge of stores electric charge in an electric field. A capacitor is a passive circuit element that has the capacity to store electric charge in an electric field. It is widely used in electric circuit in the form of filter. Yes. The voltage to current relationship for a capacitor is governed by the following equation. So this is the equation for voltage to capacitance, okay, or current to capacitance. So whilst current is constant, the capacitance changes with respect to voltage. That's what is there. I equal to capacitance dV dt, or voltage is equal to 1 over capacitance, okay, whilst current changes with respect to time, plus voltage voltage will be constant here. So where capacitance, where C is the capacitance measured in farad, and V, that is 0 volt, is the initial voltage or initial charge stored in the capacitor. When V is equal to voltage, that means a small change is equal to voltage. Constant voltage, that's dV dt equal to 0, and I equal to 0. Hence, a capacitor acts as an open circuit to DC. All what you have to learn here, it's also in regards to the type of capacitor we are talking about. Okay, the type of capacitor we are talking about. In this case, I've seen that the capacitor we are talking about is an electrolytic capacitor or polarized capacitor. So to a polarized capacitor, right, DC voltage is 0. That is why you see where V, small v, is equal to big V, which means that the voltage, the constant voltage, is a DC voltage. If it is a DC voltage, then the capacitor will be seeing the voltage as 0 completely, and it will be an open circuit. You get it? It won't have any effect on the voltage. But if it is an AC voltage, right, it doesn't become open circuit again. Okay, it becomes a closed circuit, because now it's going to store the AC voltage and release it as charges. You see that? So capacitors work with AC as filters. That's how come amplifiers require filters to filter your voice. Your voice is an AC signal, it's not a DC signal. Will anybody tell me why your yes? Why is the voice an AC signal? Nobody will mind me.
So, so when you speak, wave is generated.
Thank you. That's
So
all. It generates waves. Every wave, once it's a wave, whether it is a smooth wave or rough wave, it's AC. There's alternation in waves. Once there's alternation, it's AC. When it is DC, it's direct. So let me make it, for example, if you have a rise in tone and a fall in tone of your voice, that is AC. But if it should be constant, moving constant without any break, without any rise and fall, that is DC. I want to stress on this one so that you will remember something, okay? You see that when you want to blow a pipe or a fluid, is it flute? Flute. You want to blow. When you blow without closing the holes, right? Without putting your hands in the holes, it's air that passes. It keeps passing. There's no change, right? But as soon as you start pressing, changing the hose, you see that the pitch starts changing. I mean, the tonation starts changing. That gives you a rise and fall of the wave. That is AC. Okay. All right. So we move on to impedance. So we go to inductance. An inductor is a piece of conducting wire, generally wrapped around a core of a ferromagnetic material, like capacitors. They are employed as filters as well, but the most well-known application is their use in AC transformers or power supplies that convert AC voltage levels. An inductor, simply put, an inductor is an electrical device that converts electric energy to electric field. Okay, it builds electric field. Please note this one. Okay, it builds electric field. So it stores the energy as an electric field. There are two things. Let's see. When you connect when you connect an inductor to a capacitor in parallel, do you know what you have created? You have created a resonator or a tank circuit. A resonator is a device that generates waves at the same time charges. So let's see what happens. The inductor leads the capacitor, which means that the inductor will build field first. It is fast to build a field. Of course, it's faster than the capacitor because building the field is faster than charging. It takes time for the capacitor to store the charges. A time is taken, but the field is faster to build than the charge. Please pay particular attention to this. So what happens is that whilst the field is building, right, the capacitor, let me first say that whilst the capacitor is storing electric charges, right, this one is turning the energy that is also receiving into field. So whilst the capacitor is charging, the field is collapsing. And whilst the field is building, the capacitor is also discharging. You see that? So with these two phenomena, we are able to build what you call a transmitter. A transmitter, that's all. Only these two components put in parallel to each other is enough to build a transmitter. That's the end. So you get an amplifier, connect you to these two. Usually people use a transformer and then add a capacitor to it. They have just built a wave. That waves will now be transferred to an antenna. That is when you get the sinusoidal waves being generated. So this is how it behaves. You see, V, we are talking about the voltage to current ratio. V equal to L, which represents the inductance. Okay, V equal to inductance. Whilst current is changing, that means current is flowing through. Okay, dt, whilst time is also increasing. And current in the inductor, look at that, is inversely proportional to the inductor. So that's why we have current is equal to 1 over L. Integral of V dt plus I equal to I being 0. So this is a symbol of the inductor. It's a wire wound inductor. You have types of inductors anyway. This is a wire wound inductor, and this is a symbol. Okay, it looks like a resistor, but it's not a resistor. So now we go to linear and nonlinear elements. Linear and nonlinear element. Linear elements show linear characteristics of voltage and circuits and currents. Linear characteristics of voltage and currents. That is, its voltage current characteristics are at all times a straight line through the origin. So when we say something is linear, it means it's consistent. Okay, whilst from the beginning it's consistent, as it was, so it is. It doesn't change. So it will change the behavior. It will be the same. Examples include the current passing through a resistor is constant. It doesn't change. This is proportional to the voltage applied through its, and the relation is expressed as voltage current, or voltage is equal to current times resistor. In other words, you can say voltage is proportional to current. So whatever current passes through the resistor is equivalent to the voltage that supplied it. Of course, if they say cement is 50 kg and you lift the cement, you feel the effect of the load, or you feel the effect of the cement. The effect you are feeling is a current, and it should be proportional to the supply or the load. I mean, yes, it should be proportional to the weight of the cement. Likewise, if you go and lift something lighter, like you lift a book, the effect it will have in your hand is proportional to the weight of the book. That is linear, because the voltage that is supplying the current through the resistor should be proportional to the voltage itself. So that's when we have these examples. A linear element or network is one which satisfies the principle of superposition. Yes, the principle of homogeneity and additivity. Resistors, inductors, and capacitors are the examples of the linear element, and their properties do not change with a change in the applied voltage and the circuit current. So even if we should increase the current, or we should increase the voltage, the resistor still permits the same volume or the same property, the same amount of current will flow through. It will not restrict the current that is coming unless it goes beyond the resistivity or the resistance of the current. I mean the resistance of the resistor. Two amps. You understand me? It's giving us 2 amps. When you increase the voltage from 5 volts to, let's say, 20 volts, right? The current it's supposed to give, that's exactly the current it will give with respect to the input. So if I increase the current also, the effect of the current at the other side of the resistor will still be the same, unless the resistance is broken. Please, you get me? Now let's go to nonlinear elements. The current voltage characteristics of nonlinear elements. They do not follow the linear pattern. The current passing through it does not change linearly with the linear change in the voltage across it. So example, if we take semiconductors, for example, like transistors, diodes, okay, you see that for example, diode, when you are passing in voltage or current in a direction, right, you see that the amount of current that will flow at the other side of the diode will not be proportional to the supply of the current. At a certain point, it will either release large amount of current or a very small amount of current. Their characteristics are not the same. When you keep increasing the voltage, the supply voltage, it will get to a certain point, it will go and then release large amount of current at one time. So we say it is nonlinear because their characteristics are not the same throughout the cycle. Then we move on to bilateral and unilateral elements. An element is said to be bilateral when the same relation exists between voltage and current, for the current flowing in both directions. So let's see. We have voltage source, current source, resistance, inductance, and capacitance. The circuit containing them are called bilateral circuits. An element is said to be unilateral when the same relation does not exist between voltage and current when current flowing in both directions. The circuit containing them are called unilateral because it's moving in only one direction. We have vacuum tubes, that's an example. Vacuum tubes, silicon diodes, okay, solenoids, and then rectifiers. This is like a valve, okay? Unilateral is like a valve. So when current passes through, it cannot come back from the other side. Meanwhile, for bilateral, when current passes through, it can pass through and come back. So a perfect example is a resistor. You can get current flowing through from one lead to another, and then from the other lead to another. So this one becomes bilateral, okay? Then we have lumped and distributed elements. Lumped means cluster, and distributed, I mean, you understand distributed. The lumped elements are those elements which are very small in size, in which simultaneously action takes place. You see, simultaneous action takes place. So it means that a lot of things happen in the lamp circuit. The typical lamped elements are capacitors, resistors, inductors. Distributed elements are those which are not electrically separated from Can you please hear me? Can you hear me?
We can hear you,
Yes,
sir. We can hear you, sir.
Something just happened though.
we are seeing MTN.
I don't know what happened. So distributed elements are those which are not electrically separated, separable for analytical purposes. For example, transmission lines has distributed parameters along its length and may extend for hundreds of miles. The circuit containing them are called unilateral circuits. We have types of sources. In this, we are going to learn the sources of energy. Sources of energy. So you have independent and dependent sources. If the voltage of the voltage source is completely independent source of current, and the current of the current source is completely independent of the voltage, then the sources are called as independent sources, meaning current does not depend on the voltage, and then the voltage does not depend on the current. We will dive deeper into this. A special kind of source in which the source voltage or current depends on some other quantity in the circuit, which may be either a voltage or current anywhere in the circuit, are called dependent source or controlled source. It's nothing difficult, it's nothing strange. Okay. There are four possible dependent sources. Four possible dependent sources. Voltage dependent voltage source. Current dependent current source. Voltage dependent current source and current dependent current source. We'll dive deeper. Look at this. This is the first one. Okay. We have current dependent current source. So current moves in, right, and supplies current at the other side. You see, so this is a current that is depending on an input current. So current depending on current. Then we have voltage dependent current source. So this current or this voltage depends on the input current. This voltage, I'm at the extreme right side. Okay, extreme right side at the top. The voltage dependent current source. So you see there's a voltage, a supply voltage. Okay, this voltage is creating a current. Okay, so we call it voltage dependent current source. Then at the other side, left hand side, down bottom, left hand side, we have voltage dependent voltage source. You see that? Voltage dependent voltage source. All right, so this is a symbol, and we have current dependent voltage source. You see that? So a current moves in, and then it provides a voltage. So voltage dependent current source. This is a symbol as well. Now we are going to dive deeper. The constants of proportionalities are written as P, G, A, and R. Okay. In which B and A has no units. R has units of ohm. That's where we derive the Ohm's law from. Okay. G G units of M horse, that's mega horse. Is it millihorse also? Yeah, that's millihorse. Independent sources actually exist as physical entities, such as batteries, a DC generator, or an alternator, but dependent sources are used to represent electrical properties of electronic devices such as operational amplifiers and transistors. So I wanted to wait till this place, then I will give you an explanation. What you're talking about, when you buy a power supply, a universal power supply, maybe for a lab or something like that, you will see these symbols. You will see these symbols. That means that, let me take example, a fridge guard, or a voltage regulator. That would be the best. A voltage regulator compensates for voltages. So it means that, should it be that it's supplying current, but then the current is not sufficient to start a device, there's some form of compensation to help augment, to achieve that current. So for example, if you have a transistor attached to the supply, and then the current being supplied is not enough, it will have to give another current from a different source. Okay, or it has to convert voltage to current in order to get some amount of current to add to, in order to make up the source current. Okay. Ideal and practical sources. So we have ideal sources, which is mainly theoretical, and practical sources are actually things that are happening, or these are real. An ideal voltage source is one which delivers energy to the load at a constant terminal voltage, irrespective of the current drawn by the load. So that is an ideal situation. So we have a constant voltage source, like a battery. Let's say 12 volts. It supplies 12 volts. No matter the amount of current it's supplying, it's still 12 volts. Okay. An ideal current source is one which delivers energy with a constant current to the load, irrespective of the terminal voltage across the load. So you see, we can have a device supplying, let's say, a voltage regulator, supplying current of 2 amps, and you are using it to charge your phone. So your phone charger is also an example of a current source like that. Irrespective of how much the voltage is increasing, still it will supply exactly the 2 amps. It will not change. You see that? Now, a practical voltage source always possesses a very small value of initial resistance. That's by practice. So if a battery, for example, a dry cell is rated 12 volts, 12 volts, that's a rating, is rated 12. The value of, if you should measure the if you measure the voltage using a meter, you may not get exactly 12 volts. You may not get exactly 12 volts because it has internal resistance. Internal resistance. For the electrons to move through the battery wires, the chemicals, okay, to cross all those barriers before it will get to the tip of the meter, there's already some amount of resistance. That's why we call it internal resistance. Okay, they also will knock against each other and also move through some chemical lattice points before they are released. So these are all causing opposition to the motion of these electrons. So we call it internal resistance. That's a practical situation whereby it's mostly ignored. The internal resistance of a voltage source is always connected in series with it. And for a current source, it is always connected in parallel with it. As the value of the internal resistance of a practical voltage source is very small, its terminal voltage is assumed to be almost constant within a certain limit of current flowing through the load. So despite the resistance, we are still considering it to be constant. A practical current source is also assumed to deliver a constant current, irrespective of the terminal voltage across the load connected to it. So we assume it to be constant. This is it. So we have current source, okay, and then we also have voltage source. All right. So ideal voltage source connect in series. Look at that. So when you see V1 plus V2, of course, they sum up. So this is equivalent, so we get an equivalent voltage source with this. What this should tell us is that if you want to increase voltage, it becomes what? V1 plus V1. Okay, V1 plus V1, which will give you the terminal voltage, right? But if it is current, it will be in parallel so that you increase the current. We increase current by building the batteries in parallel. Then you are increasing current. The current becomes constant for a series battery. Meanwhile, the current increases for parallel circuit. So you see that. The R you are seeing here is the internal resistance. Internal resistance. So we add the voltages and we add the resistances. So we get one resistance at the terminal. So an ideal voltage source connected in parallel. So this is it. In this case, you are increasing the current. In this case, the voltage becomes constant and the current will be increasing. Look at that. You see that V1 is equal to V2. And note too, it's not advisable. It's not advisable to put two different voltages in parallel. It's not advisable. They must be the same value. And when we come to the current to the same, look at this. Because they are connected in series, the current is going to be the same. You see that I1 is equal to I2. They are the same, which will be equal to the current at the terminals. So this current will be the same. But when you put the current in parallel, okay, you are going to sum up the current. That means you are increasing the current. So anytime you want to increase current, you have to build your batteries in parallel. Then you increase current. So this leads us to series parallel connections. Okay. So we have source transformation. A current source or a voltage source drives current through its load or it loads resistance, and the magnitude of the current depends on the value of the load resistance. This is very powerful. This will tell us the reason why when we plug in an ion, okay, when we plug in an ion, there's a likelihood that the socket will melt depending on what type of ion it is, and also depending on the connection between the supply and the load. So in this case, let's take a microwave to be the load, and then let's take the meter to be the supply, or the wire from the pole to be the supply, or the transformer to be the supply. Yes, that would be better. So the transformer will be the supply, all right? And then the microwave is the load. Please note it, okay? A current source or a voltage source drives current through its load resistance, and the magnitude of the current depends on the value of the load resistance. In this case, the load resistance is the microwave, okay? And then the source, the current source, is the transformer. Now, it says that the current that will flow from the current source to the load resistor is dependent on the magnitude of the current. You see that? Required by the load resistor. You understand? So if the load resistor requires certain amount of current, and then the supply is supplying that current, the supply has been made in such a way that it has calculated how much current the load requires to work. Please note it as, I don't know your level in, as far as electrical engineering is concerned, I don't know your level, because people have personal, achievements. I don't know for you. So if I'm taking you too low, let me know, okay? And if I'm not going to your understanding, let me know, because it will not help us. If I am going too low, it will be delaying us. And then if I go too high too, it may disturb you, because you may not fully grasp the meaning of what I'm saying. So I'm trying to go as low as possible. So if it is something you're already used to, you can freely say it, then we'll continue.
Oh yes.
Consider.
Say
Mhm.
it's good. It's good. This is the
Yeah.
fundamental. This is the
Yeah.
basic. So We have to understand it so that it will help us to.
Okay, thank you.
Because we don't understand.
Okay. So let's consider this to be, let's consider the current we are talking about to be like food substances in your blood.
Hello, sir.
Yes.
Please, I want you to repeat the meter and the microwave, the scenario that you were giving.
Okay, I'm coming. Please, I'll be with you shortly, okay? I'm having running nose. Yeah. Okay, so let's continue, okay? I will repeat that side as in the supply and then the load. The supply, I'm saying instead of using the meter, let's use the transformer to be the supply. And let's use the microwave to be connected to the transformer. Because at the end of the day, the wires of the transformer leads to your home. So the microwave becomes the load that is connected to the supply. And I said, let's consider the current. The current is the effect of the voltage that supplies the current. So if the current is moving very fast, it means that there is a lot of electrons being transmitted. And I said that let's compare it to the human body that has blood flowing through it. The blood is pumped by the heart. The pumping of the rate at which the blood is pumping, the heart is pumping, that is how the blood is moving. So we can say blood current is correct to say so. We can say blood current because the quantity of molecules in the blood that makes the blood. So the current in the wire is based on the electrical charges or electrons that are moving through the wires. That's the meaning. So when you, as a human being, now you are going to biology. When you, as a human body, you are consuming food in order to generate energy that will make you, for you to release more of the nutrients that will now generate energy for the brain to function. So the brain becomes the user of the energy. So that becomes the load resistor because it is using the energy to think. The heart is the one that is pumping the energy. And that is a source. That is why it is said that the human heart, okay, no scientist, no biologist has been able to identify how the heart starts. They have never been able. They have gone into the human body, studied everything, but they have never been able to get the starting of the heart.
Sir, please,
And how?
how?
Yeah, it's the same. You
Like
see, the
how it
chemical.
develop, like how it develops, or
No, not how it develops. How it kickstarts.
uh,
You
like
understand?
like beginning of life. Let's say
Yes,
when a
let's take
child
it
is
so.
forming. When a
Yes,
child is
they know
forming.
everything. They have studied everything. They know, they understand all, and then they can regenerate and produce all that. But how it will kickstart itself, they have never been
Oh,
able
okay,
to.
okay,
That's
okay.
the only thing left. They have done tissue generation, they have done tissue culture. They can produce your organs, they can produce everything, but they have not been able to. If they can create the heart, all right, but how will it kickstart itself? That is the only thing left for them to produce a human being. I'm telling you. Let's put that to aside. It is not part of what we are studying. Now, we are saying that, you see, if the electrons are moving, sea of electrons moving, we call it electric charge. That's when we say electric charge. So the supply will supply the current depending on the requirement of the load. You understand it? So those in at ECG, when they come to the area, they count the number of houses that are connected to a transformer. What items do they use before they supply the transformer? That's why when the transformer blows, they know what blew the transformer. So far as it is not a natural disaster like maybe a rainfall or wind, storm, or something like that, or somebody tampered with it, if not for that reason, and a transformer bends, every electrical engineer understands why the transformer should bend. Because the load is demanding for what the transformer cannot supply. So it will break down. Imagine your weight. You are weighing 60 kg. Okay, that's your weight, 60 kg. And then they are forcing you to carry 2 bags of cement. Can you carry it? You can't, because your energy levels cannot supply that energy for carrying the cement.
Sir,
Yes.
please, with the cement aspect there, you can just slim someone to be slim, but the person who carry two cement, you really wonder with that.
Yeah. The person is destroying himself. He's driving his body beyond the saturation. Let the person finish, you go and be suffering in the house. You understand? He has defied the rule.
And some people too, they have weight, like as you said, like 60 kg or 45 kg. But even the cement, they cannot even carry it. Something small they
Because they have
cannot.
because they have not built it themselves, they are working below their capacity. Do you understand it?
Yes,
You
sir.
can have a well-built man, but he will see Mike Tyson, he'll be running away. You understand? Because he's working below his capacity. Should he train himself to his full potential, you cannot stand in front of him. That's why even in boxing, we have weight, you have ranks. You cannot take a light weight to go and fight a heavyweight because that is not his rank. You understand it?
Yes, sir.
So let's come back to the point I want to make here. The point I want to make is that the supply will only supply the current that the load requires. So if the load is requiring more than the supply can supply, the supply will force itself to supply that current. So as it is forcing itself to supply that current, it is damaging itself. So within a short time, it will burn. You see
Okay,
that?
sir.
Mm,
Please, I want to clarify this.
mm,
With ECG meter, the rating, do they
mhm.
rate on current or they rate on voltage? like maybe someone's consumption of electricity, do they use the meter to read the current flowing through, or they read the voltage to give you the bill or the credit that you've bought? Is it current that is drawing that power, or is voltage that is drawing that power?
Okay, in the first place, I would like to correct you for mixing two different phenomena. Okay. Now, what ECG is doing is simply the same as you have just connected a meter. Okay, you have connected a meter to a supply, or you have connected a meter to test voltage or current. That's what you have done. That's what ECG is doing. The meter you are seeing is simply a multimeter. In general sense, it's simply a multimeter. What happens is that they have connected to the supply, and then they are testing a parameter. Now, what parameter are they testing? Is the current. Because you're consuming, how much current is flowing through? That's your consumption. Now, we have to convert this one to power consumption. So we have to know the amount of voltage that is supplied at the terminal. Then we will consider the current that flows through. Then we're able to measure. So it is actually power that is measured. That's why it is reading in kilowatts. You understand? When you go to the meter, you see that it is measured in kilowatts. That is power. Power is equivalent to voltage times current. So it is taking both the voltage and then the current. Please
Okay.
understand?
Yes, sir. So
So
if they are measuring in power, then which means if the voltage drops down, their measurement also drops down.
No,
Oh.
voltage is proportional directly to the current. So there'll be compensation. You understand? Rather, I would say let the current drop. If the current drop, that is when you get a lesser reading.
Okay, so if the current drops, so which means if your earthing system is very good, the earthing system is going to help the current to drop. Is it so?
Exactly. Yes. In fact, if you have a very good earthing system, you will know the simple. It's very simple. If your earthing system is very good, you are not going to consume, or you are not going to record unnecessary wastage. The current that is coming is not all current that becomes a useful current. Some may come in as waste. And to avoid the waste, you have to avoid leakages. And you can avoid leakages by getting a good earthing system. You see that? There are a lot of things coming. Just relax, okay?
Okay, sir.
We'll dive deeper. You have to take it chapter by chapter. As we are going, you will see them coming. So, what the point I want to make here, the very important point I want to make here is that the supply voltage or the source voltage or the source current, okay, supplies current depending on the requirement of the load resistor. Okay. So let me read it again. A current source or voltage source drives current through its load. So through its load, it means that from the wire, okay, from the connecting wire to the load. That is what it means. So to its load resistance And the magnitude of it, of the current, depends on the value of the load. So if you connect a very large load, right, it's going to draw a very large current. That's the meaning. That's why if somebody is using a microwave, air fryer, and the lights in your home, and you are sharing the same meter with that person, your bill will keep increasing because it's using devices that requires a lot of current to drive. Okay, so that's all. So let's consider this. Consider a practical voltage source and a practical current source connected in the same load resistance as shown in figure 11. So let's look at this one. The first one is a voltage source, okay, and driving current through internal resistor. Okay, this is an internal resistor. The first resistor is an internal resistor. So that resistor is very negligible. The voltage that reaches the load, right, is direct. Right? Meanwhile, the current is not the same. You see that? We have the load current. And then the current moving through the wire. So the current that moves through the wire is directly proportional. It's the same as the load resistor. It's the same as the load resistor. And then look at the current source. The current that passes through. You see that there'll be current for the load resistor and then current for the internal resistor. You see, a practical voltage source and a practical current source connected to the same load. R1, R1 in R1s in figure represent the internal resistance of the voltage source, that's Vs, and current source, that is Is. Two sources are said to be identical when they produce identical terminal voltage and load current. The circuit in figure represents a practical voltage source and a practical current source, respectively, with load connected to both the sources. The terminal voltage, that is VL, and load current, that is IL, across their terminals are the same. Hence, the practical voltage source and practical current source shown in the dotted box of figure are equal. The two equivalent sources should also provide the same open circuit voltage and short circuit current. So this is the mathematics behind it. Don't worry about this one. Okay. So we go to resistance, inductance, capacitance parameter. So we say RLC. We need this topic a lot. This, what you are entering right now, please don't joke with it. Okay. Now we will try to avoid the mathematics as much as possible. So we'll not be doing the integrals. Okay. Where I will tell you to take seriously, you take seriously. You will not be doing the integrals. These ones are not necessary. Okay. Let me see. Yes, I can hear you.
Hello, sir.
Yes. Hello.
So please, with the mathematical aspect that, hello, sir, please can you hear me?
Yeah, I can hear you.
Okay, so with the mathematical aspect, if we ignore it, is it not going to affect us in any way, or it's normal?
No, it's not going to affect you. The issue is that this mathematics, as in integration, differentiation, and you're already supposed to know
Okay.
integration by parts. Integration
Yes.
is in engineering mathematics. You see
Yes.
that? So
And in calculus. Yes.
yes, and now you have to, because if I start right now, there are steps that are jumped, big gaps that are jumped from here to here, and then we'll have to do the calculation, which means that if I want to focus on it, I'm only giving you something you will not have understanding and meaning of. It's just like you are going to chew and pour. And me too,
Okay.
I don't like any lesson that is chew and pour. You must understand what you are doing. Here be the case
Okay.
that I don't know whether you have been taught engineering mathematics. Have you been taken for engineering mathematics?
Yes.
You are doing engineering mathematics.
No. We did this thing, algebra, and now we are doing calculus.
So that means you have to do it.
We are doing engineering mathematics.
Then we have to do it. Then you will understand what is here. I thought you don't have any knowledge of it, then I will just be disturbing you. That's why. That means you have to do it. So let's start now, okay? Don't blame your class rep. He's doing good, okay? So where were we? No, not here. I've gone past this. So yes, so we start with RLC. That is resistance, inductance. Please, inductance is represented with L and capacitance C. Okay. So resistance. Let's talk about resistance first. Resistance is that property of a circuit element which opposes the flow of electric currents, and in doing so, convert electrical energy into heat energy. It is the proportionality factor in Ohm's law relating voltage and current. It's nice. You see this thing we have just read here. Hang on, okay? Hang on tight. I'm taking you for a journey. This thing we have just said here right now. Let me tell you that the white man studied human beings to do everything they do. In fact, they study nature to do everything they do. You see, the blood is the current. Like I said, the heart is a source that pumps the blood. So the heart is a generator. Then the blood is pumped through the blood vessels. So the generator pumps electrons through the wires. Okay. Now, if the wire, you use a certain grade of wire, for example, you use 2.5 cable, and then at a certain point, you use, you connect 2.5 cable to, let's say, a flexible wire. Then you continue and go and connect 2.5 cable to the flexible wire elsewhere.
The fur. The dog is the fur. That's why.
Mr. Philip, please can you mute yourself for us?
That's
Can we go on? So,
Yes, sir.
what I'm talking about is like a closed loop, okay, one loop. So you cut, let's say you cut the wire and you fix in a flexible wire in between. What do you think will happen? Practically, I want to ask you, what do you think will happen? Assuming there's a wire from 2.5 cable, okay, that connects to your fridge. Then you cut the wire into two. Then you piece in a flexible wire. What do you think will happen?
So
The
the
current
flexible
can
wire will
flow.
bend.
The flexible wire will bend, right?
Yes.
Okay, that's good. And when it bends, it will open circuit, right?
Yes, it will open.
Yes. So this is what happens. The steady human being, oh, the heart is the pumping power and pumping the current through the vessel, the capillaries, whatever. When it gets to a point that the wire is so small, the pumping energy will not say that the wire is small, so it won't pump. It will keep pumping it. And then the wire, because it is thinner, small, it is offering opposition. This is the opposition we are talking about, the resistance. It will force itself to be supplying, but the opening is too small. At the end of the day, it will burst. You see that? It will burst. So you have to supply, you have to use resistance that are equivalent to the supply in order to let the flow keep going on. So resistors are meant to supply a specific amount of current and limit some amount from exiting. So it's not a complete opposition or stop. No, it doesn't stop the flow of current. As a lot of people misunderstand it and think it stops the flow of current, as in offering opposition. No. In this type of opposition, it's actually limiting it to a certain degree. You see that? So hence we have rating of resistance. That is what we learned earlier, that we have grades of resistors. So if you have a resistor that is rated 10 kilo ohm, 10 kilo ohm has a certain amount of current it will permit to pass through it. If you have a resistor that is 1 kilo ohm, it also has a certain amount of current it will permit to pass through it. So if the current coming through is larger, way larger than the resistor can bear, either the resistor, if it is the current is increasing and the resistor cannot permit all, it will be heating up. The elements will be heating up. So to be heating, when it goes to a certain threshold that it cannot bear, to burst, that's where the resistor can blast. Every material also has resistance. Likewise, human beings having tolerance levels. There are some things somebody can tolerate, some foolish things, nonsense things. Another person cannot. That is the person's resistance. You see that? In total, we call it impedance. To be able to resist pressure. When the electrons are moving through the resistor, they are mounting pressure on the resistor. If it can hold that pressure, it will hold it and permit it to be passing. If it cannot hold the pressure and becoming too much, the energy he's using to block the current, okay, the excess current from reaching, it is making it become hot. When the energy is too much that it cannot bear, the pressure is too much, it will burst, it will get damaged. It's like people forcing a gate open. The door is small, there's stampede, and people are entering. There's no time for order. that one should go first, second, third, and fourth. There's no time for that. So they are all rushing to open the door. They will break the door. So the resistor will be opened. So the capacity for the resistor, or the ability for the resistor to oppose this force, is called ohm, because it was discovered by somebody called George Ohm, and then he named it after himself. So the unit becomes ohm. Yeah, sir. Ohm's law states that the voltage drop across a conductor of given length and area of cross section is directly proportional to the current flowing through it. You see that? You see the cross section? That means that if the wire is thick, it is expected that more current can flow because a lot of content that will flow. That is, the electrons are plenty on it. So as soon as you connect wire to it, a lot of current will flow. Likewise, the length is also considered. The longer the length, I did not understand this concept until I had an experience. When I was young, around let's say 12 years old, yes, I went to a place whereby they manufacture blocks. I went there alone, curiosity. No, they put a 10 on the machine. Like there's current flowing through the machine. I don't know whether it was deliberate or not. Meanwhile, I used to be curious, so I'd received multiple shocks from switches because I could open a switch and get a shock and then be trying to fidget, using a tester to test the current, seeing the power in it and all that. Until one day, when I went there, I went to the block factory. That was around Sunday. They were not operating. And current was flowing through the machine. I didn't know. And I went and held the bar. This one, it was not shock, no. It was electrocution. I received a shock I've never forgotten since that.
Yes, like this one is greetings. This one is greetings.
I was vibrating. My luck was I shouted as soon as thing happened. And one thing about electricity is that when it shocks you, the thing you do last, that's you keep doing it. I shouted and then I was vibrating. It was lifting me up. And that's when I understood AC. Because afterwards I went and sat down. When the thing happened, I didn't just let go. I was imagining why it happened to me and how I behaved. I was deading on the floor, which means that I was going with respect to the alternation. You know, AC alternates 50 hertz. That's 50 times in 1 second. So I was bouncing on the floor like that. 50 times in 1 second. Because I was shouting, my voice echoed in the area. Like that. And I was bouncing until one guy who used to operate the machine, he lives just nearby. When he heard that, by God's grace, I don't know whatever came into his head, he rushed to that place and turned off the machine. It was even better when I was there. When he turned off the machine threw me like this in Kung Fu, this in Shaolin soccer. You see how they can kick somebody, the person will flying. That's
Yes, sir. Yes, sir. Yes, sir.
So you have a good experience.
I tell you, this is a life experience.
Yeah.
That's when I understood AC.
That's a welcome. Welcome to the word.
See, it's pure energy. You understand? And it is related. So if you go and load your house with so many gadgets, it's expected that you have increased your load resistance. You have increased the load resistance, and the supply has no chance than to supply what you require. So you are going to melt down your changeover, your switch. You're going to melt down your switch because the supply from the pole, right from the transformer, it comes to your exchange. I mean your switch, which is the, what do you call it? Is it a changeover? No. Oh, there's a name for it. There's another name for it. That's the first entry point. So you see that you'll be there and
Sir,
your house
please,
will be,
the first entry point, is it in the distribution board or
it's in the distribution board.
is it the how do you call it? The incomer?
No,
Either the two pole breaker or the three pole, four
no,
pole breaker.
yeah, there's a name for it. It's usually attached to the meter. In fact, the meter is attached to it.
What? So they cut out.
There's a name for it, apart from cutout.
RCB or MCB?
Yes, it breaks. Circuit breaker, that's the name.
Circuit breaker.
You understand? It breaks automatically. This just these days that they have made it that way. Those days it wasn't like that. You have to go and turn it off yourself. And when your demand is higher than it, right, it will melt. And they will have to come and change the whole thing for you. Luckily, because of advance of technology, it will break on its own. You see? So usually what happens is that if your house load is more than the circuit breaker will melt. Then you go and call the electrician. Electrician will come because he's not an engineer. That's the difference between engineers and then technicians. Because the electrician only knows how to fix and does not know the mathematics behind it, you go and buy a different one and come and fix. Sometimes it's the same thing you buy. He doesn't understand that your load has increased. So you go and buy the same thing and come and fix. It won't keep long. When you turn on the fridge, you turn on the microwave, you turn on the freezer and some air conditioning, then it will go again. And you have to go and change. Anytime, Sunday, every time Sunday, your circuit breaker will go off. Then you should know that your usage or your demand is beyond that of the circuit breaker's rating. So that means you have to go and increase the circuit breaker, the ohmic value of the circuit breaker.
So with respect to that, what if you are using, the consumption is low, but you use a circuit breaker with a higher arm? Does it have any effect on the consumption?
No, because you are still within.
Imagine a two-bedroom house is consuming about 63 amps. And we install 120 amps for the house, or 200 amps, or something like that.
When there's a surge, over voltage,
okay,
it will sip in straight.
Sip in as in, can you break it down for us?
Sip in as in, that amount of energy will go into your house straight. So when it happens that there's a fridge on, you understand? There's fridge on. There's maybe devices that are connected. that are not able to use that energy. They will receive that energy to damage them.
So you mean the arms of the breaker shouldn't be more than.
It will be too much because you don't need it. That's why you don't need to use a three-phase meter or a three-phase meter. Once you are not using, you don't need three-phase. You'll be billed higher.
So which means the consumption will be higher, but you are not even using
You are not
it.
using it. Yes. Let me give you an example. You see, you'll be there and lightning. How come lightning can pass into your wiring and damage your gadgets? You understand it? Because you don't have a good earthing system, and then you don't have lightning arrestor. You see?
So with that, when you have a good lighting system, you have a lightning arrestor, and the arms of your incomer or the RCB or MCCB or something like that is higher. Are you safe?
Yes, you are safe because lightning arrestor will arrest the lightning straight into ground.
But you said earlier that the consumption, if the arms is higher, because you don't need it, it will rate your bill to rate higher.
No, what I'm saying is that lightning arrestor is different from your electrical wiring. You know that. So the lightning arrestor
Yes,
will
sir.
arrest the lightning straight to ground, which will not affect to prevent the lightning from tampering with your electrical wiring. You understand? But what I'm talking about as the surge is energy from the cables. That is your transformer. There are certain instances you will get over voltage instantly. For example, assuming we are all on the blue line, for whatever reason, everybody turns off his house, which means, and yours is on. Once they stop all that, that means that all the currents are coming to you. You understand?
Yes, sir.
Uh-huh. So in that case, when your your circuit breaker is rated in such a way that it allows in large amount of current without breaking, that means all that current will come and arrest your fridge. Hence, you need a fridge guard to protect your fridge from that current, excess current that is coming. You see that? And when the excess current comes to, if your cabling cannot take it, your fuse will blow. And if you are somebody,
Sir, if hot cannot take it.
if your cables, your fuse will blow first. That's why you have fuse there. So when your fuse blow, you are free. If your fuse is also direct, you didn't connect fuse and it's direct like that, that means that the current will go and arrest the motor. So it will let the motor run over its capacity. So the motor will burn. When electricity is shocking you, I told you, I have a practical experience. If electricity is shocking you, it's nothing that is happening to you. The only thing that is happening to you is that the electricity, the current is going to arrest the generator that is in you. It will superimpose it. That means that it's going to it's going to capture the heart, your heart. It will capture your heart because your heart is the only vibrating element in your body that is pumping the blood. So it's going to force the blood to pump backwards.
50 times in 1 second. That is going to run an engine of 1.5 times in 1 second. So it will shut it down. You see, this is the reason why you are electrocuted. It's like you are using a drilling machine, or let's say you are using a cutting machine. I know you who are practical people, so you'll be appreciating what I'm saying. You are using a cutting machine, and the cutting machine you are using to cut, let's say, wood. You are using a small cutting machine to cut, let's say, odum wood. The very good example is, you see that drilling machine that the carpenters have been using to bore hole in wood. They are of different rates. Some are big, some are small. And you force them go and use a small one to drill a hole in odum. Take one, let's say, they'll have a name for it. The beam. You are drilling a hole through a beam. You will drive the machine beyond its energy. So it's going to bend the machine. The coils are going to bend. The same way, when that excess current seep through, and then you don't have a fridge guard, you don't have a fuse, it will straight go and arrest your motor to let the motor overrun, so it will bend the coils. You understand? Please, if you want to contest, you can contest too. Hello?
So, for me, I understand, but
Hello,
I don't know
yes.
if Kingsley understands what you are saying.
Oh, me, I understand.
Ah,
I understand, ma'am. I understand now.
okay, so let's proceed then.
Because a practical example, like I want to
Yes.
come in. Say a practical example is like using your blender.
Hmm.
And maybe the blender is
Hmm.
supposed to take maybe 4
Nice one.
liters
Nice one.
of maybe your vegetables. Then
Mm-hmm.
you put in maybe 6 liters. The motor will
Hmm.
be able to blend. Yeah, it will either your motor will either shut, or the coil or the windings inside the motor will get bent.
Will bend. Hmm.
Yeah,
So that's it. Okay, so
yeah.
hence this will help us a lot. So when our lighting system, when our lights goes off in the house, we'll have a fair idea about it. Have you realized that in electrical wiring, home wiring, for example, you are not supposed to be having knots. You are not supposed to be having knots. Join wires, join wires, join wires. You are not supposed to have that. If you are
Sir,
using a
please,
straight wire,
what's the
try.
reason?
We hear of it and other things, but practically, the proving, we need to be proved. That is for
Hmm.
me, from one side. We hear of it,
Okay.
it's not good, it's not safe. We as
Hmm.
fire safety, we know it causes, if there's a loose contact or something like that, there is a friction in the cables which
Hmm.
causes heat. For the heat to generate to cause like burning of the insulation and other things, with that, if it
Hmm.
touches any combustible materials, it ends up in
Hmm.
burning. That is where fire starts
Okay.
from.
Yeah.
At electrical
Yes.
aspect, that is
Okay.
that is.
Operator.
Take answer.
Okay. Okay. So now this is the electrical aspect. Okay. Now, you see, we said that the supply current as the load resistor requires. So the magnitude of supply depends on the load. So where will the current pass? It will pass through the cabling. Is that it? So
Yes,
if you
sir.
have more knots, If you have more knots, it means that a knot is combination of two same wires. You understand me? A knot is a combination of two same wires. So if this is 1.5 and this is 1.5 and you are knotting, which means that point alone becomes what?
That
You
that
3
understand
point
me?
mm.
become 5 or
3 mm.
No. 3, good.
okay.
That point becomes 3 mm, which means it can take in more current.
Okay.
You see that? It will take in more current. So there's going to be inconsistency. So the more the knots you are creating, the more inconsistencies you are creating. Hence, there'll be excess current in your circuit. Excess current. So at a point, the current here will increase, and at a point it will decrease. At a point it will increase. At a point it will increase. You are causing heating and wastage in your electrical wiring. And the secret is that current passes through the path with least resistance. Current passes through the path with least resistance. So wherever there is a knot, more current will flow through that place.
Oh, okay.
Where will it exit? It will exit through where there's less, where there's, it will definitely pass through the thin wire. So this becomes example as in connecting a thin wire in the middle of a thick wires. It's example like that. So what happens is that there'll be heating in the system. And when electrical wire, when there's current passing through wire, there's also a magnetic field. The current that is flowing is generating magnetic field and electric field. These two things, there are always three things moving. Current will create magnetic field and create electric field as well. So because of that, it can cause wastage of current. Hence, you get a higher billing. And if you're not careful, and then the wires are the brush type, okay, and then you use the insulation tape to tape it, you think you are free. When the heat starts, the house I am in right now, when the electrician was wiring, he wired and you got to one particular point. The wires got free. He forgot. I don't know what happened. He forgot. So he had to make a knot over there, thick knot. Whenever the sun becomes hot, and then you could see that the light this thing. If you want to know whether you are operating on a high current, your lights will tell you. At a point, you see your light becomes very bright, and to go dim sometimes. When it becomes very bright, and I go to that corner, I feel heat. It's like something is burning over there. That's the only point. Only point. You feel the place is burning. You have that kind of, you see when current is passing through iron that is burning, you can smell some burn,
Yeah, you can
though it is
smell.
not burning.
You then you have
Yeah,
that
you can smell it.
you have that fishy smell.
Yes. So I always go and stand there and see that, well, that's the cause of it. Excess current. You understand? So that's it. Electricity is very interesting, to be frank with you. If you want to talk, we'll talk. So to verify Ohm's law, we say current is proportional to resistance. Okay, current is proportional to yes, current is proportional to resistance and proportional to voltage. Okay, hence we have V equal to IR. V equal to IR. Under Ohm's law, we are going to learn about conductance and resistance. And we learn about conductivity and resistivity. So, power, you see the let me read here. Here, the reciprocal of resistance is called conductance, okay, which is represented by a G. The unit for resistance is ohms, and the unit for conductance is MHO, which is Siemens. Okay, Siemens. When current flow through a resistive material, heat is generated. You see, I said it. Heat is generated by the collision of electrons with other atomic particles. The power absorbed by the resistor is converted to heat and is given by the expression power equal to VI, which is also equal to I square R. Please remember, it is not I2R, I square R. Okay, I square R. Where I is the where where I is the current, okay, the amps, and V is the voltage across the resistor in volts. So you say energy loss in resistance, which is the heat. So heat is dissipated. So we will also refer heat. So the W, okay, and we say that equal to is equal to power. Okay, the integral uh, uh, maximum value for the power dt, okay, dt, which is equal to power I square R is the energy, and then T. Because we are integrating T, so we call it PT. This is power in time equal to I square RT. Then we say it is equal to V squared over RT. Now we are supposed to do calculations for all these things. Let's move on. Inductance. I already told you that inductance build fields. Inductors build fields. Inductor is the property of a material that by virtue of which it opposes any change of magnitude and direction of electric current passing through conductor. A wire of certain length, when twisted into a coil, becomes a basic conductor. A change in the magnitude and the electromagnetic field. Please, an inductor. Okay, I said already that when current is flowing through a conductor, it possesses both magnetic field and electric field. Okay. To increase the magnetic field or to convert all the energy into magnetic field, there's a way to turn the wires so that the current that is passing through it will change into a magnetic field. The same way, if there's current passing through a wire, there's a way to change the current so that it will change to heat. By placing a resistor, right, we can change all that current into heat energy. The same way, when we place an inductor, we can change all that current into magnetic field or electric field, and that becomes its inductance. Simple put, again, it's like when when current is passing through a wire, we can turn that current into full energy by connecting a fan to it so that the fan will be rotating, right? The same way we can connect an iron to it, then the iron will produce heat. The same way we can connect microwave to it for it to cook for us, fridge to turn into ice for us. Yes. The same way we can connect an inductor to it. The inductor's property is based on its ability to change the energy from the current, okay, into ability to make it charge or create charges. Simple. What is charges? The charges are just atoms that are either negatively charged or positively charged. That's all. Increase in current expands the field. Of course, we know when the current is increasing, the field will become bigger. And decrease in current reduces it. A change in current produces change in the electromagnetic field. This produces a voltage across the coil according to Faraday's law of electromagnetic induction. Because of that, we can generate electricity without contact. This is where we got the transformer from. Okay. I don't know whether we will have face-to-face or we'll be having labs. If not, we would have created a wireless charger by using coils. You can create a wireless charger. That's when you appreciate how electromagnetic is used to transfer power from one point to another without contact. Okay. So these are the equations associated with it. Induced voltage is equal to the length of the wire, okay, the derivative of the current per time, okay, the I dt. So which means that with respect to the voltage and the length of the wire, and the inductor, the inductor depends on the length of the wire, okay, we will have current, all right. So where V is voltage across the inductor in volts, I is a current through inductor in amps. So we have this. So we have the integral of the current is equal to the integral of the voltage times 1 over L. So in summary, we are going to take only this one. V equal to L di dt. That's okay. The induced
Yes, sir.
voltage across the inductor is 0.
Sir.
Yeah. Yes.
Yes, sir. Like I wanted to
Hello.
bring to your notice this. Like the last one that you give us the formula. So I see in the slide that they have proof the formulas, and then then at the end of the day they give the original equation or the formula. So if you can be giving us the formulas, if they derive it, then you give us that this is the final formula, so that we'll be keeping this one.
Is it? Oh, I can't hear you. Hello.
Hi.
Can you hear me, please?
Yes, sir.
Yes, please.
Okay. I want us to get to catch up slow, then we stop. Okay.
Okay, sir.
I believe we will meet face to face, right?
Yes, sir.
Yes, sir.
That will be once.
So the day, yes, the day we meet face to face, then we do all the calculations. Okay.
Ish. Sir, calculations, mom. Because we think maybe that day, if maybe you have some practical,
Let me
or
calculate you,
or you don't have any practical in this
Section.
We'll have
um,
practicals, but still we'll do some calculations. Okay.
Okay.
So let's conclude. Let's conclude here. The current in a capacitor is 0 if the voltage across it is constant. Do you accept it? Do you accept it?
Sir, please, can you go over?
You say that the current in a capacitor is 0. Current in a capacitor is 0 if the voltage across it is constant. Is it true or false?
sir, sir, first.
Why a capacitor?
Sir,
Hello. This is the reason why this
sir, please, your line is breaking on.
the network has started misbehaving.
He's talking now, sir.
Sir,
Yes,
sir,
I know.
it's not supposed to be 0.
Yes.
It's not supposed
Why?
to be 0 because
There cannot be. Okay, so
because voltage is the pressure that pushes the current. So whenever there is voltage, there must be current.
Okay.
So even if the voltage is constant,
I disagree
there
with
must
you.
be current flowing.
You need with the voltage, you need
I
the
will agree
current.
with you because of one reason.
You need the current.
I say that
What?
I will agree with you because of only one reason, because they didn't specify the type of capacitor it is.
Okay. Okay. Yeah.
Okay. For a ceramic capacitor, you will still get voltage across. You will get voltage, but you will not get current. So even it still holds. For a
Okay.
polarized
Okay.
capacitor,
Okay.
you get zero current.
Yeah. Yeah.
You get zero current because if the voltage is constant, there's nothing moving up and down. And capacitor only works on up and down movement, change in voltage. You understand it? Yes. Hence, it becomes an AC. It's not constant. It's constantly moving up and down, up and down, up and down. Because of that change in the voltage, that is why you are getting capacitance. If there's no change in voltage and it is direct, which is constant, there's no change in voltage, then it will be nothing. That's why capacitors don't regard, polarized capacitors don't regard DC. Okay, a small change in voltage across a capacitor within zero time given gives an infinite current, yes, through the capacitor, which is physically impossible. In a fixed capacitor, the voltage cannot change abruptly. A capacitor behaves as short circuit just after switching across DC voltage. The capacitor can store a finite amount of energy, even if the current through it is zero. You understand? So when you connect a capacitor to energy source, right, it will store the energy. If you take hey Charlie, to be able to reduce their consumption, but there are prices to be paid if you do that. Some people can connect capacitors, large capacitors, okay, to the electrical systems by some means and be able to reduce their consumption because of the way the system is billing you. You can have a way to
So so that should be
I know Kingsley,
a power
Will
factor
ask
for us.
questions. Yes. I know Kingsley will ask questions.
So
We'll talk about that one
the
later. Okay.
capacitor ideology
The
that
price
you are
you
talking about,
pay.
that should be a power factor for us.
The price you pay, because what you use for that connection is the earth wire. The earth is the mother of all electrons. All electrons goes to earth. So if you go and use the earth for that, you get current, you get power, all right, which your billing or your meter cannot detect. Note, electricity is only by potential difference. This side should be high in potential and this side should be low in potential. So if you are having high potential here and high potential here, you can measure. You understand? If you're having a high potential here and a high potential here, but they are not equal, and a small change in potential, you still enjoy the electricity, but you cannot measure the exact amount of electricity you're enjoying because the potential at both sides are high, but only that the change is different, a little different. You see, most of the times when you are checking blood pressure, they say they check the systolic and then the diastolic. Is that not it? The difference between it is what will let you know whether you are having high blood pressure or not. The difference between the diastolic and then the systolic, that's when you see that you have problem. So even if the systolic goes high and the diastolic also goes high proportionally, if they are proportional, you don't have a problem like that. But if they are disproportional, you have a problem. So ECG is measuring your consumption based on the difference in potential. So if you're able to close the gap and you make the gap slim, you enjoy the energy all right, but your bill will become very small. Sometimes people can even do it to yourself, you will not even get the billing at all. It will be like a whole year, then they'll read a little for you. But the danger comes if there should be any surges, if there should be any lightning, that will seep through. Where is the earth that will run the current down to ground for you? You have used the earth already. ECG is billing you on the neutral line. Is that not it? So anytime because the neutral line is expected not to have current, it's only a return. So anytime there's current supply from the neutral, from the other side, or simple put, you have used the earth as your neutral. You understand?
Yes, sir.
Mm-hmm. So you use the earth as your neutral. When there is a surge, it will burn your house.
But say,
Mm-hmm.
when I use the earth as my neutral and it is serving me well, can I bury another earth at a different place, not the same place? Oh?
Earth is earth. Earth is earth. Unless you do something to it first. That's why people are burying capacitors. There's a new device
But
in town. The Chinese have created a new device. And then they are encouraging people to use it, buy it and use it in their house. You connect it as if you have connected a meter to your house. It's a type of system like that. And they said it is just going to, it's just meant to correct your consumption. So let's end it, okay?
Hello, sir.
Hello. Yes.
Say,
I said let's end it here. Okay.
okay.
But if
But
you have a question, you can ask.
Please,
yes, I have a question. Okay, Bernard.
Mm-hmm.
please, what I want to say is that like this course, I think we have a lot of thing to do. So if you can
Mm-hmm.
make it happen, maybe Friday for us to catch up on what you have to do. If that one will be
On
okay
Friday,
for us. Yes.
that means it will be Friday evening.
Yes, sir.
So I want you to discuss among yourselves, okay?
Okay, sir.
Mm-hmm.
And then even the weekend, if we can get a different weekend so that we will be meeting instead of this time, because this time it clashes with one of my classes. It starts actually from 8:30.
Okay, sir.
Sir, sir.
Yes. Mm-hmm.
So we have discussed that since we have 2 lectures with you one day, like today example, if it will be possible that we will move one to Friday evening so that it will be like today, like Saturdays we'll be having one lectures and then there's Friday you have, so that it will not be stressing you too.
Okay. That will be very fine with me. It should be this one, circuit theory. Okay.
Okay.
Let's move the circuit theory to Friday. Okay. By the
Okay,
time
sir.
I will leave it with you. I will leave the time with you so that you guys will discuss. But it should be in the evening.
Okay.
Sure. So thank you for coming. Okay. God
Okay, sir.
willing. Hey, we will still have the engineer. Let's discuss this right now before we close. The engineering technology.
Yes, sir.
I mean, sorry, the
Drawing.
the engineering drawing. Yes. You see, we are not going to have physical meetings like that. So it's going to be based on softwares.
Okay, sir.
Okay. I'm going to teach you software, and the same software we are going to use to learn the circuit theory. Okay. So I'll introduce you to KeyCard. Okay. KeyCard. I'll introduce you to I don't know whether I introduce you to Tinkercad.
Key card.
Did I introduce you to Tinkercad? Yes, I did.
Yeah,
When
yes,
you
sir.
came to the lab the last time. So we will start with the Tinkercad, and we use the Tinkercad to solve problems that are related to circuit theory. Then I will introduce you to multisim. Okay, multisim. We use multisim to solve network problems. Like I'm going to start with Ketchup's law right now. Okay. Then I'll introduce you to every circuit. So our engineering drawing is going to be is solely going to be softwares, simulation. That's supposed to be the engineering drawing. No, that's supposed to be engineering drawing, electrical engineering drawing.
Okay, sir.
Now we don't do draftmanship, whereby you'll be carrying drawing board and be drawing lines and no. Okay. And if I introduce you to AutoCAD is mainly for mechanical engineering. You see, but since
But
you are
sir,
doing electrical, yes,
but sir, sir, we have AutoCAD electrical.
yes, we do. I know we do. Which
Okay.
these ones will do the same. But the AutoCAD, I don't know whether we'll get. It's also online, right?
Yeah, but
Sir,
difficult
yes, sir.
It's very heavy. That's why AutoCAD and MATLAB, they are
Yeah,
very heavy.
yeah, very, very heavy. But sir, I
Mm.
have some light one that I'm using.
The cracked one, eh?
Yeah, the crack one. I'm downloading it.
Okay, so let's see about that one too. Okay. If I have to add it, I'll add it to it.
Yeah,
Okay,
sir, but
so
we have we are,
mhm.
most of us, some of us don't have laptops, so maybe the card one can help, because some of them you can do it on your phone, although it's not advisable.
Yes, that's why I'm introducing the every circuit too.
Mm.
That's why I'm introducing the
Hello,
every
sir.
circuit. Every circuit it's a mobile application. Yes.
Please,
Mhm.
we have 3 minutes to meet Dr. Fakwa.
Oh, okay. So we have
So
to
I'll
wait.
play the two. As we'll be meeting right after him. Then if the so it will not be like we've tempered his time or something like that, then maybe he will be waiting for us another
Yes, I
time.
understand. All right,
Okay.
sure. Okay, so later. Yeah, bye.
Thank you,
Okay.
sir.
You can turn it off, okay?